Alrighty, so just to recap the Annie walking in a circle problem and the Ferris wheel problem, for those of you that have been absent, or if you just kind of want to recap when you get your papers back to see where you went wrong or what you did right. So just to recap, for the Annie problem, I'm going to start with the second part on the back, which you're supposed to check in with me after the first part. And I gave you a new starting point now for Annie. So instead of starting out at 36.0, she now started at a different point. Some of you got 75 zeros, some of you I think I gave 72 zeros, so it might have been a little bit different. But in any case, she started at a point that was further out on the x-axis. Everything else remained the same. The radius of her circle was still 36. She took 60 seconds to complete a cycle, hence 60 seconds is the period. Okay, period is how long it takes to complete one rotation, and she's still traveling counterclockwise. So if we can actually kind of graph the circle that she's walking on, we see that she's starting out here at 75.0. And I know if I draw a circle that my circle is going to come back around and it's going to stay on the positive side of the x-axis, because I know that with a radius of 36, that means that the diameter is twice the length of the radius. So the diameter is 72. So 75 take away 72 brings me to 3. So 30 is going to be the point where she is back. Her y-coordinate would be 0, but her x-coordinate would be 3 at that point, halfway around the circle, or at 30 seconds. So let me just kind of draw what looks like a circle a little bit. Alrighty, so if we kept track of some, again, the function asked you to come up with a function that modeled her x-coordinate over time. So her time is the independent variable, and her x-coordinate depends on how long she's been walking for. So this is your dependent variable. It depends on time. So first of all, we know that at time 0, she's now 75 units away from 0, 0. Since she travels still for 60 seconds, we know she's going to be back at 75 after 60 seconds. And then along the way, the easiest places to mark off would be at the quarter marks, because we can divide 60 into 4 chunks of time. So after 15 seconds, she's here. So her x-coordinate we see would be halfway between these values, or if you think about it, 36 units to the right of 3 or to the left of 35. So this is going to be 39 is going to be her x-coordinate. Her y-coordinate, of course, would be 36 high. But all we're tracking in this case is the x-coordinate. So at time 15, which is 15 seconds into her walk, her x-coordinate is 39. Then, if she continues to walk, after 30 seconds or halfway around the circle, we saw that she was going to reach an x-coordinate of 3. She traveled for another 15 seconds, which is 45 seconds. We see she's going to reach this point, which is the same x-coordinate as she was here, so it's still going to be 39 for your x-coordinate. And then once she gets all the way around 60 seconds, she's going to be back at an x-coordinate of 75. So for this problem, it asked you to write a function for this travel, and of course we'd keep repeating. If I added another 15 seconds on, after 75 seconds, she's going to be back at 39. It's just going to keep going 75, 39, 3, 39, 79, or sorry, 75, 39, 3, and so forth. So let's just go ahead and now not graph her path, but track the relationships between time and her x-coordinate. So I'm going to mark off my time here. 0 after 15 seconds, after 30 seconds, after 45 seconds, after 60 seconds. And I'm just going to graph one period. We could keep going. All right, it ranges anywhere from 75. That's going to be my highest. So, and then I have, and that's as high as it goes. As low it goes is 3. And let's just mark 39 somewhere in here. Halfway between those values. So 0, 75, 15, 39. After 30 seconds, that's when she hit a low of 3. At 45 seconds, she was at 39. At 60, she was at 75. And again, like I said, if we kept going around here, she'd be back at 39, and it would keep repeating its values. Hence, we have and it would keep repeating, we have a trig function here. So in this case, on the front side, we ended up graphing the same scenario, but it was at 36, 0. And it went from 36 to negative 36 because she actually went on the other side of the x-axis. So basically we see we have the same graph, it has the same period, it has the same amplitude. The distance from the bottom to the top is still, so this is 375, the distance is still that. We have to divide that. Our midline is still 39. Okay, so we go from the below midline is 36. If we go another 36, that brings us back up to 75. So we see that our amplitude is still 36. Our period is still 60 seconds. The only thing that's midline is no longer at 0, it's up at 39, which means that there's been a vertical shift. So our k value shifted up 39. So in this case, our equation is just going to be f of t, could be any variable there. Our amplitude is 36, and we see we have a cosine function. So we have cosine. And then I have to figure out my b value. So again, to figure out my b value, I know my period is equal to 2 pi over b. So if I solve that proportion, let me go and bring it over here. 60 over 1 equals 2 pi over b. Cross multiply, you get 60b equals 2 pi. Divide by 60. So we get 2 pi over 60, or you could reduce that to pi over 30, t. And then our vertical shift was up 39. So, sorry, I was off the graph, off the screen. So that was just Annie starting at a different point. For the Ferris wheel problem, which was, let's see the second part here now, it said, now instead of walking, now imagine that Annie was riding a Ferris wheel. So we're going to take this basically the same idea, but now we're going to look at it as her riding a Ferris wheel. So we see here that this is basically her height off the ground. So we know that as time goes on, right, your position changes. So what's the radius of the wheel? Well, it's the same radius, nothing changes, so our radius was still 36. The maximum height of the wheel was here, so it was 75 feet. What is the minimum of the graph? The minimum here graphs after 30 seconds, she would be 3 feet off the ground. So in case it was just the lowest point on the ride, or I should say the height she is above the ground at the lowest point on the on the ride. Okay, so when she comes down to the bottom, she ends up, the closest she gets to the ground is 3 feet. The next part, what is the average of the height of the wheel? Well, if the max is 75 and your min is 3, to find an average you add the numbers and you divide by 2, so that's going to give us 78 divided by 2, and what do you know, it brings us to our midline here of 39. So 39 was the average. Angular speed, by definition, are the radians, so your angle in radians traveled over a given amount of time. So you could use any of the angles that you guys went. You guys can convert these times. You could say after 15 seconds, which is pi over 2. It took her 15 seconds, so you could do pi over 2 divided by 15, or you could do after pi radians. You know that when she traveled here, it took her 30 seconds, so you could do pi over 30. That would probably be the easiest, so I would probably take, I know when she traveled pi radians, it took her 30 seconds, so this is pi radians every 30 seconds, or this is equivalent to saying she traveled pi over 30 radians per 1 second. Okay, a lot of you guys took her full circle, so she traveled 2 pi radians, which was a full circle, in 60 seconds. and if you reduce that, you get back to the same answer. Linear speed. So this is same idea, but this time it's the distance she travels. So the distance along a circle is theta times r's arc length, right? So if she traveled 3 radians and the radians were 4 feet, then she traveled 12 feet over time. So in this case, let's go ahead and take, let's just take the first one. So we have pi, and we know a radian is the length of the radius, which is 36. Took her 30 seconds to complete that. Oh, and this is 36 feet. Let me zoom in here. So in this case, we see that we can divide both of these by 6, so that would leave us with 6 pi over 5 feet, and this was per second. So again, that can be read as 6 pi feet every 5 seconds, or it can be looked at as 6 pi over 5 feet every 1 second. Both of those are the same thing. So if you have more questions about this, you're going to get back your tide problem. The tide problem really requires you to do a very similar thing as we did on these problems. Basically, to track the 2 things that you wanted to compare for the tide problem, it was time and the height of the tide. So coming up with a table, which a lot of you guys did, putting your points, observing if it's a sine or cosine function, deciding on your amplitude, deciding what your period is, from there figuring out your b value, figuring out if there's a vertical or horizontal shift. With the tide problem, we'll talk about it on block day, but there was a horizontal shift required because it asked you to start the time at midnight. So it's just like here, if I asked you to start the time after, and we had done this in class, what would be this function if I started the clock after her first 15 seconds? So basically, if we started the graph here, well, we see that really that would be equivalent to taking the graph that we have now, but just shifting it to the left 15 seconds. If we shifted this whole graph to the left 15 seconds, that would basically start at time 0. That would be her after 15 seconds. So if we shifted this whole graph, this point would get moved here, which would be a starting point. So basically, you'd have the same function, but it was shifted to the left 15. So you'd have cosine of 2 pi over 60, and then you'd have t, and to the left is positive plus 15 plus 39. So this would be the case if we were to start at a different time. If we were to start at 15 seconds, we'd have to move that back. So anyhow, that's how the tide problem related when it asked you to start after midnight, because originally I think our starting time was 8 o'clock. Most of you started your max. But anyhow, I'm not going to get too much in the tide problem. We'll talk about it later. But if you're struggling with this, feel free to come in and just work on it. When you come in, please just don't say, Ms. Schaaf, I don't get it. Say, hey, Ms. Schaaf, all right, here's where I'm at. And I understand, and then describe to me what you understand and then where you're getting stuck, where you're not knowing how to go on. So that's the best way to approach it. When you just say, I don't understand, I know that there's something you know about the problem, so I want you to at least have a starting block for our conversation so that I can more specifically help you and see where you at least have an understanding and then where you might have a misunderstanding. So please be patient with this, but you know, if you struggle with this, come in, ask questions, just please don't hide from it. Anyhow, I will see you guys tomorrow.